Okay, hello. Hello, good afternoon, hello, good afternoon, or good morning, or good noon time, depends where you are. But I'm excited to continue learning about physics, specifically more on vectors. I think we have like 2 more sections left before, but my internet kind of sucks, so I kept getting errors on my YouTube end, so hopefully the stream is fine. And let me pop out my chats. I kind of did have to rush a little bit because I took too long to eat food again. I ate like pork ribs, and I also had chicken and pasta and cucumbers. Don't ask me why that combination is. I kind of just made whatever I had in my fridge, and so that's what I had. And I also had like some leafy greens, some spinach as well. Alright. Let me pop out my chat. Okay, nope. There we go. This one. It's this one. Okay, sorry. We'll go to here. But yeah, yay! Hello! I like your little emote. Is that like a zombie? Looks super cute. Was it spider? I hate spiders. But like not all of them. Cute ones are okay. But the real life ones scare me. First, hello. But yes, we'll be learning the algebra of vectors. So last time we learned I think like the operations of vectors. Our coordinate systems. Oh, right, the coordinate systems. Because we talked about like 2D and 3D. And we learned about how you can use like geometry to find the length of the vectors with the sine and tangent and stuff like that. And then we learned about displacement and how you can translate a Cartesian plane into a polar coordinate system. Yeah, and we have 3-dimensional one. Could measure the displacement of a drone. Yeah, I kind of forgot. It's okay. We don't need to know the knowledge. You know, it's fine. But yeah, I guess this stuff is important. We just know how to label them correctly. We know that we can use geometry to figure out the length of a vector. It's a spider monkey. Oh. Blueberry. Berry. Good day. Good day, strawberries. Yes. I still need to like find someone to commission the little mascot. I've drawn it out. I just need to find someone to commission it. And I've been saving up for it, so I think it should be okay. Okay, well, first let's start with the algebra of vectors. So our learning objectives of today, of this section, will be applying analytical methods of vector algebra to find the resultant vectors and solve vector equations for unknown vectors. So the resultant vector is just like the result of a operation. So like if we find the displacement, we say it goes here and here, and you kind of do like the addition or whatever of it, and you find that displacement. That is the resultant vector, and then we can interpret physical situations in terms of vector expressions. Vectors can be added together and multiplied by scalars, so this is a singular value, and remember that like a vector has two pieces of information. So it's got a scalar value, which is usually its magnitude, and another value, which is its direction. Robo-Kuma. Yes, I am! I'm a Robobot. I like your funny words, magic lady. Thanks! Hello and welcome. Okay, so let's first learn about the properties. So vector addition is associative and cumulative. Cumulative, yeah. So you can like switch it. And vector multiplication by a sum of vectors is distributive. Also, scalar multiplication by a sum is distributive. So maybe I will quickly go over these two equations and then we'll move on to this distributive property. So we'll write all three. But that, here. Question, what is a scalar? A scalar is a singular value in a way. So it's got like one piece of information. A vector has two pieces of information. So, let's say something is going like how fast. Like let's say a car is going like, no, that's not me, that's not right. Hold on, let me think. Oh, here we are. So let's say velocity is 40 kilometers per hour. There's an example right here. So that in itself is a scalar. However, with a vector, you can say it's going 4 miles or 4 kilometers per hour, but in 4 directions or 4 degrees south. Like something like that. So that would be a vector. So a scalar has one piece of information, and it could be like weight or how fast something is going. So something that has some sort of magnitude. But a vector will describe where it's going. Thank you for the follow, Skrittles? Is that how you say it? Okay, so we can say vector addition. This is the quick review. Associative. Vector addition is associative, and I'm just gonna click on this. See. So we can have that example where basically you can move the parentheses around when you add. So I guess it doesn't matter which way you add. By the way, so I use this like arrow as a vector to denote a vector. Oftentimes you'll see it bolded, but because I can't bold while writing, I will just write the arrow on top. It is also addition is also commutative. So you can swap around the vector values. So it's kind of just like any addition for this case. Scalar equals a single variable. Yeah, sort of. Like a single value. Yeah, so single variable. Vector addition. Oh, however, multiplication is scalar distributive. It should be multiplication. So basically, when it says vector multiplication, I'm just gonna call it multi and put a dot. So once you multiply like a singular value into the vector, it is distributive. So in this case, they have alpha 1, and then you have a, and then alpha 2, and then you have the a vector again. And because these are scalars, if you like, they don't have the arrow on top, you can write like this. Yeah, okay. And then we'll go back to where we were. This was a long time ago, I kind of forgot. Oh well, that's why I'm a failed engineer for a reason. Alright, here we are. Also, Also, scalar multiplication, so we put scalar multi by a sum of vectors is distributive. I'm actually really interested in this because I understand most of what you're saying. Okay, that's good, that's good. I just finished an algebra class and went over these types of things. I don't know if it was in the curriculum or the teacher was free balling. That's good. I hope you do understand. But if you don't, like, this book is completely for free. It's like open source. Hence why I can do this. Because if I were to use a textbook that is not open source and not like I'd be running into copyright problems. Sorry if my brain is a little bit slow today. I did have a migraine and I did take a painkiller for it. But it's okay. Happens all the time. So, in this property, it's kind of like the backwards property of the first one. I'm not the first one, the one above it. So they're kind of like the same, but it has to involve a scalar and a vector. So you can take the scalar, take two scalars and like take them out as long as the vectors are the same. So you have A, and here. And then if the scalar is the same, you can take out the vectors and then it's equivalent. Yeah, okay. In this equation, in this equation, A is any number, a scalar, for example, a vector anti-parallel, so like anti-parallel to vector A, and it's written like that in this form. Can be expressed by simply multiplying the A vector by the scalar -1. So an anti-parallel vector is just multiplied by -1. So we can write that. For anti-parallel, multiply, so I'm gonna put multiply vector with, we'll just have that as like the scalar symbol since this book seems to be using that a lot. Scalar -1. Then we get this. And then we'll put like that example. So we have A little hat. So this hat represents that's the directional component. So here we have the magnitude component, which is like the AX, the AY, and the AZ. And then for the like direction component, we have the the I hat, the J hat, and the K hat. Let me move this a little bit. Okay. And then we have an example already. So let me switch to green color, a better looking green color. I don't like that green color. We have example 2.8, direction of motion. So in a Cartesian coordinate system where I denotes the geographic east, J denotes geographic north, and K denotes altitude above sea level. Okay, so we have, like, let's draw a little compass. And we have I. Oh, I'll just write like little I there, and then J here. And then K is sort of like going above. We'll have like K here. This is like the flat compass. Yeah, I can't really draw or use a tablet, so please ignore that. But here we have the K-hat. Above sea level, a military convoy advances its position through unknown territory with velocity of that. If the convoy had to retreat, with what geographic direction would it be moving? So it's going with that velocity in that direction. Okay. This way. This is our vector. Professor, I'm sorry I'm late. Please don't block me. I need the class to pass. If you don't pass this class, I guess you should just pass away. Wow, I can't believe you're late again. How dare you? Into the vacuum chamber for my next experiment. I love your little emote. Dr. Boo, no! Ah! I love that emote so much. Alright, sorry. Wait, where did my pinned message go? Oh, it was you! I was like, huh? Alright, thank you. Okay. The vector, the velocity vector has a component, has the third component, this, which says the convoy is climbing at a rate of 100 meters per hour through the mountainous terrain. At the same time, its velocity is 40 kilometers per hour to the east and 30 kilometers to the north. Okay, so what each of this piece of information tells us is where it's going, how fast in that specific direction. I'm gonna go like from left to right, so I'll go 4 kilometers per hour east, 3 kilometers, so that would be north, and 0.1 kilometers up. Because this is just straight up going up. Up into the sky. Up to the sky. Okay. Then we have that. So it moves on the ground in the direction of this. Right, so because it's like this, so if we take this part of the compass and you make sort of this like triangle from it, we have the north side here, so that would be 3. Then we have the 4. And then we can find the angle. So hold on, let me think. Let me think for a second. Like tangent, the angle is equal to, should be this leg, oops, this one over this one. Because we have the opposite, right? This is the tangent angle. I think that's the tangent angle. Is this the tangent angle? Hold on, give me a second. Yes, it is. I'm right. I'm correct. I remember correctly. Okay, this is the tangent angle. Then we get 3 over 4. And then you can do the inverse tangent of that, which is what they're doing. And they get 34 or 37 degrees. Ugh. I can't read. I don't have my calculator with me right now. But I'm just gonna say that it's probably correct. I mean, it's the book. It's a textbook after all. Let me move this up so my ears are not blocking. So it's going this way. So this degree is 37 degrees north of east. North of east. So that's like this description. If the convoy had to retreat, its new velocity vector u would have to be anti-parallel to this. So to this vector. So in order for it to be anti-parallel, like what we learned earlier, we just multiply it by a scalar of -1. A scalar value with like a -1, or that scalar value is equal to -1. So the one right above this, right here. So we're using that property. So we can take this value and essentially just multiply everything by negative and then add that sort of scalar component in front. So we can do that. So yeah, that scalar component in front. Got 4 I hat. That should be -3. -3 j hat. -0.1 and then k hat. And then we keep the units as the same. The negative sign of the third component indicates that the convoy would be descending into the ground, I guess, or it seems like they're on a mountain, so I guess it would be going down the mountain. The direction angle of retreat is that. So instead of going north of east, you sort of like flip it. So the opposite of north would be south, and the opposite of east would mean west. I'm lost. What does the hat mean with the angle? So this sort of tells us direction. So how do I say this? So this number tells us how fast it's going, but this is sort of like describing where on the compass it's going. So it's going 4 kilometers opposite of our eye, and they said that our eye denotes the geographic east. So we have east as I, and then it's going the opposite of that because it's negative, so it's going west. So they are unit vectors, and then they describe, they're sort of like they describe where it's going. Does that make sense? Oh, I get it. Okay, good. Sorry, I'm not the best. Are unit vectors for x, y, and z axis. Yes, exactly. So they describe where on that sort of coordinate system, in this case is Cartesian, but then we relate that Cartesian coordinate to directions, where it's going. So we have that, and it's going the complete other way. So we got 37, so the opposite of north is south, and then of west, because the opposite of east is west. Therefore, the convoy will be moving on the ground in direction of 37 south of west while descending on its way back. So it's going down the mountain at 37 degrees south of west, while the initial one, the first one that is not retreating. Oh wait, no. So it goes up the mountain north of east at 37, and then it retreats and goes down the mountain at 37 south of west. So basically just turns around and goes backwards. Alright, the generalization of the number 0 to vector algebra is called a null vector. So we're back to the notes section. So let me get my blue color and then let me move this up so my head is not blocking. Denoted by 0 for all components of the null vector are 0. So a 0 vector, then we have all the unit vectors being 0. So there is no length and absolutely no direction because they're all 0. The two vectors a and b are equal vectors if and only if their difference is the null vector. So if we subtract the two vectors, and then they're sort of like their resultant is equal to a null vector, and then that means that they are equal vectors. So basically, if you take something that has a value of 5 and then you subtract that by 5 and it's 0, you know that this and this is equal to each other. So like, let's say x, y minus 0, and you know what value of x is. That must mean that y is equal to 0, but in this case, we relate that back to vectors. So if you subtract the two and you get that null vector, then they are equivalent. So let's write that down for part of the notes. So a null vector. Null vector. We'll have the big 0 with the arrow on top. And then the components are 0, 1, I, plus this, j. I can never get the dots on the i's and the k's correctly. They always look so horrible. I don't know why. I should hat these, because I can't bold them. Okay, and then if we have two vectors, so two vectors, spelled that wrong, vectors, two vectors are equal if difference is null vector. And see, difference is null vector. Yeah, okay. This vector equation means we have simultaneously ax minus bx is equal to 0, and then the same for all the other components, for all the other parts of the plane, so the x, y, and z component. Hence, we write a is equal to b if and only if the corresponding components of vectors a and b are equal. So, if corresponding components are equal, a equal to vector b if components of vectors a and b are equal. I need to remember how to draw the ampersand. I always forget. Okay. I always forget. Hold on. Give me a moment. There we go. That's really bad, but yeah, ampersand and b are equal. Are equal. So we can write that bolded or that highlighted key point and a z is easy. Yep. Two vectors are equal when their corresponding scalar components are equal. So, corresponding scalar components have to be equal as well. I'm gonna abbreviate that, are equal. Yep. Okay. Resolving vectors into their scalar vector components, in other words, finding their scalar components and expressing them analytically in a vector component form, allows us to use vector algebra to find sums or differences of many vectors analytically without using graphical methods. So basically we can just find, we can use vector algebra, we don't need a graph, and we can just do it based on math. based on just like operations. For example, to find the resultant vector, the resultant of two vectors, wow, I cannot read. We simply add them component by component as follows. So this is our resultant. We add the components together. Okay. So we can add them by the components. Add by components. And I'm not going to write that whole line, but I will write this. I will write the sort of component part. I'm not going to write that second part. So we got ax plus, that's an x, not a y. Bx, then we got the I hat, plus ay plus by, get j hat, and then we got az plus bz, and then k hat. There we go. In this way, by using equation of this above, scalar components of the resultant vector are equals this. They are the sum of the corresponding scalar components of vectors a and b. So basically this will now equal rx I plus ry j and rz k. Yay! This is our resultant vector. My head's not blocking it yet. By the way, this happens often. Sometimes I will like write down here and then my ginormous head will accidentally block it. And I won't notice because I won't be able to see it. No, I got rid of the smile. But my ginormous head and my ears won't be able to see it. So yeah, please tell me if that happens. Analytical methods can be used to find components of a resultant of many vectors. For example, if we are to sum up n vectors, f1, f2, f3, and then so on, all the way to whatever variable you want to finish, there are where each vector is this, the resultant vector, so fr is equal to the summation of all of it. Here too, okay. Let me take this in for a little bit. Think of it. Okay, oh, I see. So basically, if you keep doing this many times, don't be scared by the summations. Basically what it's saying is if you have a bunch of vectors, so let's just say vector a1, you will keep like adding it. So you'll keep on adding it. You have vector a1, a2, like a3, and you want the resultant of however many it goes. So it's like 3, and then let's say you have like 100 of them. You would just keep adding all of your 100 vectors together, and then you will get that resultant. So in this case, they called it like FR. You'll get that. So if you just keep adding it, this is a summation. Please don't be scared by like the summation symbol. But yeah, that's what that means. So you can sort of represent it by just keep on adding however many components. Slams head on desk. No, don't do that. You're fine. Don't worry about it. It's not that bad. I hope at least like you're understanding something, because that's my goal. If someone learns at least just like one thing, then I'm happy. They don't have to understand it all, because to be honest, I don't understand it all. But if someone understands something, then I'm happy. And hello, you have like butterflies in your name. That's pretty. I like butterflies. I like to look at butterflies. When butterflies land on me, I get scared. But I like to look at butterflies from afar. Therefore, the scalar components of the resultant vector are this. So if you want to add multiple vectors, like more than a few, add multiple vectors. Add multiple vectors, then you sort of can represent it mathematically with the summation symbol. Does everyone know how to read this summation symbol? Like, I can explain it if not. Because I think when the first time I saw a summation symbol, a long time ago, a very long time ago, it does look scary, right? You see it in all like movies, and it's like, what the heck is that? But it's actually not hard to read. Please explain. Okay, I will. Let me just write this down, and then I will explain how to read a summation symbol. It looks scary, but it just means like you have to add a bunch of things. We got N, we got our summation symbol, A1. Y. I'm just gonna write it like this. R, and then we got FZ. N, K1. D. All right. So, you're getting PTSD. No! Don't get PTSD. Okay, I'm gonna write this a little bit bigger. So this means a bunch of adding. A bunch of adding. I just came to follow you and say hi. I need to study to my test. Bye-bye. Thank you for stopping by and saying hello. And yes, do well on your test. I'm sure you'll do great. So this just means you're gonna add a bunch. So, yeah, okay. This is what this symbol initially means. Up here is how many times this you're gonna add. So, or I guess what number Up to what number are you gonna add? Number you're going to add. We hit a follower goal? Hello! And thank you for the follow. I appreciate it. Are you my 130th follower? Congrats. What number you're going to add? Hi, hello! It seems I am. Well, welcome. Welcome to the strawberries. Anyways, that's what we call our little community. So I'm Blueberry, and community name is Strawberries. But yeah, so this describes what number we're going to add, and then this will tell us what number we're going to start at. Starting number. So they're just like kind of three things that you need to like understand from this. So the way that they sort of wrote it out is they have K1. I'm not gonna describe this in terms of vectors. I'm gonna just use like regular terms. So we'll have like, I'll just call this x. So this is some value, and then you have x1 or k. So for this, you will have x will keep adding. So you have x1 plus x2 and all the way till you hit that number n. Telecommunications engineer, good luck. So you keep adding that all the way to hit the number n. So let's give n an actual value. We'll say like 5. Oops. We'll say like 5. That's a 5. So we have x1, x2, x3. Then you keep adding all the way till you hit x5 plus. That's a plus. That's a plus. x5. And then this is now equivalent to just adding all of that together. Yeah. The summation symbol is the Greek letter sigma. So it is sigma. I was thinking, like, I always forget Greek letters. All the time. I always forget what, like, it kind of like looks like squiggly. I think it's like zeta. I think that's what it's called. I always forget that one. I have a test on Wednesday. Well, good luck on your test on Wednesday. Uppercase. Yes, this is an uppercase sigma. Okay. Does this make sense when you see this sigma symbol, you see the summation symbol that you just keep on adding until you hit the number at the top. So let's just say that this is like 2, then you'll just get rid of this. And you start at x2 and then go all the way to x5. But yeah, I will look for now because I have to study. I have to see an engineer VTuber. Well, good luck on your test. I'm sure you'll do great. And thank you for stopping by. I appreciate it. So yeah, that's how you read this summation symbol. It's not that scary, it just looks scary because it's a Greek letter. But you just keep adding. It's basically a bunch of adding. Okay, having found the scalar components, we can write the resultant vector component form this. And we get that as our resultant. Oh, I forget, I can't scroll in this. So basically, all of this equals to fr vector, which is equal to frxi hat plus fry hat and frv Hey hat. Yeah. Let me zoom out a little bit. So that hopefully you can see it better. Analytical methods for finding the resultant and, in general, for solving vector equations are very important in physics because many physical quantities are vectors. For example, we use this method in kinematics to find resultant displacement vectors and resultant velocity vectors. In mechanics, to find resultant force vectors and the resultant of many derived vector quantities. In electricity and magnetism, to find resultant electric or magnetic vector fields. So basically, you can use vectors to describe a lot of things, and it's good to be able to add them together to represent a value, and it can be used in electricity and magnetics, as well as kinematics. I suck at kinematics, and yet we are here learning kinematics. Alright, we have another example. So I'll switch back to the green. Scroll up a little. Whoa, this example is so long. I hope we finish this section, but we'll see. So we got example 2.9. 3 displacement vectors. So we got A, B, and C as a displacement vector, and their specified magnitudes are 100 or 10. Why did I say 100? 10, 7, and 8. They're whole numbers. And he put decimal points, and I didn't see that decimal point, so my bad. By the respective direction angles in the horizontal direction of alpha is 35, beta is negative 110. And then we got, what is this? How do you say this? Mu? Is this a mu? That's not a mu. Okay, whatever this Greek letter symbol is named. 30 degrees. The physical units of the magnitudes are centimeters. Okay, so these are all in centimeters. Centimeters. Resolve the vector to their scalar components and find the following vectors. So if you want to add them all together, you want to subtract a minus b, and as well as do this operation. Gamma. Alright, thank you. Gamma. So alpha, beta, and gamma. Then we have the s vector, which is a minus the scalar value of 3 times b plus c. First, we use equation that to find the scalar components of each vector, and we express each vector in its vector component given by another equation. Then we use the analytical methods of vector algebra to find its resultants. So I'm assuming that these two equations are just the sine and cosine equation, so I'm not going to go back to them. But yeah. So this is 30 degrees, or 35. Sorry, this is 30 degrees. And then this is negative 110. They're all in centimeters. So to find the x and y component, use the whole like geometry thing. Or you can just use the equation. But yeah, to find the scalar component, the x, y, and scalar component, use the geometry to use cosine and sine to find it. So we got ax is equal to a. So a is that 10. 10. And then if we want to find the x, no, I didn't mean that. What is sine again? So we have, oh, x, y, I'm just gonna call this z. X, y, z. I forgot it is opposite over, so the x over the z. And then we got cosine. Physics problems are just combining equations until a number reveals itself. Yes, it's combining a lot of, a bunch of math, and then you kind of apply that to some problem, and then the number will eventually reveal itself, usually. if it's only theoretical. When if you ever get to experimentation, nothing ever works out, but what program do you use to paint whiteboard thing? It is just Microsoft Whiteboard. At least that's what I use. I know there's like other things out there. I heard Krita is very nice. I use Krita to make my shitty drawings. To make my horrible drawings. But yeah. Then we get this angle. But I use Microsoft Whiteboard for something like this because it's simple. Something like Krita will give you more options to move things around, but since it's just math, I just, you know, really simple. I don't do anything fancy with my notes. I've seen people do really fancy stuff, and that's cool. Yeah, okay. So we get, oh. What? What happened? I can't go back? Should be 35 degrees. And then I'm not going to calculate this because I don't have my calculator with me. But we'll have this. I'll just trust their calculations. So, like, if you ever study on your own, I would highly suggest actually doing the problems and actually punching the numbers in your calculator if you're genuinely studying for it. Or studying for something, just in general. And don't be like me and just copy the answer, because I don't have a calculator with me. But basically, you do this for all of them. So we got bx 7 cosine -10 -110 degrees. Then they got -2.39 centimeters. And then you just do it for the rest. So you get all of these as your answer. Don't forget, friction and air resistance are a myth. Always ignore exactly a frictionless surface. Who needs air resistance? Anything else? Nah, just ignore that. Yes, that's how I remembered the sine cosine thing. It's been so long that I forgot it too. I also was taught with like SOHCAHTOA and then TOA with like the opposite and hypotenuse and adjacent, but it's genuinely been so long that I forgot. So with this, we can get our resultant vector. So you basically just add a bunch of the AX's, the BX and the CX together. AX plus BX, which is what you get from like doing all this. And then I'm just gonna write 12.73. Hello, hello! Did they teach you the unit circle? They did. Listen, I'm old, okay? It's been a long time. I also just tend to have a horrible memory. So, yeah. Listen, I may not have failed engineering yet, but also, do I certainly feel like a failure. You're old, no way. Well, I call myself old. You know, it's been enough time where I feel like I'm comfortable saying this. Should I? Yeah, I will say it. I actually have a degree. But I'm still in school because I'm trying to get more degrees. I'm a lot older than people might expect. Okay, I've not reached, like, you know... I've not reached the age supremacy of other certain VTubers just yet, but... I have a degree. What degree do you have? I have a degree in engineering. And yet I still think like this. But yeah, I basically went back to school to get a higher level degree. So, I still, this is also why I went back. I feel like a failure regardless. Did I finish school a while ago? Yeah. but I'm still stupid. Okay, so we got part A. So this is our resultant. Now let me go over it since I didn't write it all out. And why is my back button not working? Like, it doesn't matter what happens, I will always feel like a failure. Honestly, I felt like school did not at all prepare me for work. Hence why I went back. And also, apparently, if I go back, I can get more money later on. But we'll see. But this stuff I have not touched in years. Like, it's been so long. It's almost been, well, it hasn't been a decade yet, but it's been a really long time. I just do this for fun because I think it's fun to refresh. It's fun to, like, look back and think, huh, I do remember that. Or, yep, I don't remember that. But, okay, let me go over part A. So this is our A answer, which is just the resultant of all three on a 2-coordinate system. So first we get our magnitudes. So we get 10, 7, and 8. Then we get our direction. So these are the degrees. We can get the scalar component of the AX and the scalar component of the AY. Same with the BX, you can get that, and the BY and CX and CY. You do that using the trigonometry, or this is how it's, like, explained. Because we have the angle, but we don't necessarily have that distance. But once we get that, we can get these values. So we can get like I said, the scalar component of each vector. Then we want the resultant. And for that, we will add all the x components, all the scalar x components, and all the scalar y components. And then we can get this as the resultant. And I don't know why my back button is not working. We'll just leave the underlines there. But yeah, so that's part A of this question. We can go to part B, which was to subtract the two. We want to get a vector D. And to do that, you simply just take the scalar components, the AX minus BX, and then we get AY minus BY. You find that value, which they said was 10.58. And this one was 12.31. You get that in centimeters, and then we simply 0.58. You have the I hat. It's the 12. It's 3, 1. J hat. And thank you for the sub and the follow. But yeah, thank you. I appreciate it. I saw someone sub earlier. The thing about, like, unfortunately with YouTube, it doesn't really show up. Like, there's no activity feed on YouTube. There is, but it's hard to get that. It's not like built into the UI, which sucks. Okay, there you go. CM. So this is our difference of the vector A and B. I need to sneeze again. Nope, I don't need to sneeze anymore. Unless I do. I think I would have learned Calc 2 better if I learned the trig identities better. Oh. I forgot what Calc 2 is. Actually, no, I learned calculus probably a decade ago. I did actually learn calculus a decade ago. Yeah. Physics, I actually didn't learn physics till a little more later, but it's been so long. I'm an old lady now. Alright, so we get this. We basically take the AX, you multiply 3 by BX, then plus CX. Get that. The one where they do a lot of integrals. Oh. Trig? That one involves trig? I did. I actually used to do a calc learn with me just like this one before, when I first started streaming. But I used Khan Academy instead. I didn't like that one as much. I think using this textbook is so much easier. I don't understand anything, but this is so soothing for some reason.
Are you excuse me, student, are you telling me that I'm putting you to bed? If you're gonna be like that, you should go somewhere else.
I'm joking. I'm really lucky I never had a professor who did that. So apparently at some schools, if you sleep in class, the professor will like kick you out of the lecture hall. My professors have never done that. which is good. I think if that ever happened, I would be too scared to go to class. Not because I think I'll fall asleep or anything. It's because, like, I think them as a person now just scares me. But I remember watching some, like, YouTube video of some professor, so some student, like, yawned in the class, and the professor, like, yelled at that student, which he was like, I can't believe you're being so disrespectful to me. And I'm like, that kid is just tired. Let him be. Yeah, ever since I saw that video, I'm very lucky I never had a professor do that. I did have people like fall asleep in class, but usually the professor doesn't say anything. I think there was once someone was snoring and the professor looked like they wanted to wake them up, not necessarily because they wanted to wake them up, but because they wanted them to like stop snoring. But I could see like the mental turmoil on that professor's face, and they did not wake them up, but they were snoring. But for me, that's like understandable. But like, I don't think they should get yelled at. They should just be like, oh, if you're tired, you know, sorry, you're interrupting the class. Like, I think if you yawn, you should not get yelled at. That's just unwarranted. So basically, we could do all these operations just like regular math, just like anything, even if it isn't a vector. I don't know why my undo button is not working. Anything that like isn't a vector, and then we can get a resultant from it. So the most important part is sort of breaking down this, these vectors is breaking down the vectors into its scalar components, and then from the scalar components, all you need to do is just regular math, so you don't necessarily have to worry about direction. The hardest part, or the newest part, I guess, would be using the trigonometry of like the sine, cosine, and tangent to find that scalar component first. Significance. Having found the vector components, we can illustrate the vectors by graphing, or we can compute magnitudes and direction angles, such as this figure below. So this is what we actually found. So for part A, we got the resultant vector being this. Part B, a resultant vector is this. And then part S, we got the one right here as that. Results for the magnitude in B and C can be compared with results for the same problems obtained in the graphical method shown previously. Notice that the analytical method produces the exact same results, and its accuracy is not limited by the resolution of a ruler or protractor, as it is the graphical method used previously for finding the same resultant. So yeah, previously they told me to get out a ruler and protractor, and I did not have that. But I find the analytical method to be easier, of course, and more accurate. So another example immediately. You can do check your understanding. I'm probably not going to do it, but I'll explain how to get the answer. So we get the 3 displacement vectors, so similar to the other one. We have, so I guess you get 7, and then we get F, which is different, respectively by their respective direction angles, and that one has an angle of positive 110. The physical units of the magnitudes are centimeters. Use the analytical method to find vector G and verify that G is 28.15 centimeters and has the angle of that. So to find this, we'll do, I won't calculate it out because like I said, I don't have a calculator with me. But to find the fx component, we get 20, right, 20, and then it was cosine, I believe, yes. 20 cosine, 110. And then whatever the answer of that is becomes your fx, and then you get the same for y. So this time you just do the sine. 10. That. You get that. And then you just take the components of each. So we got a x plus 2, bx plus, or minus, and my head is gonna block it soon, so I'll move it up, minus fx, and that will equal your gx. We get our b, oh sorry, not b. No, I keep forgetting that I can't use my undo. I don't know what happened. This thing crashes all the time. I'm thinking of switching to a different software to write stuff, but yeah. So it's ay plus 2 by minus fy. We get gy. And then we get gx I is g y j hat. That is our g vector. And to find the angle, we use the tangent, which would be x, I think? No, it would be gy over x, right? opposite over adjacent. So yeah. Yeah, so we get this, and then you just inverse tangent it, and then you can check. But yeah, I think that's how you do check your understanding 28. And then we have another example immediately after. We have example 2, and I see a dog in the picture. There's a doggo. There's a doge.
Oh, it's so cute.
If they're the same dog, exactly. Alright, I want a dog, sorry. I keep getting distracted. I sleep all the time in class. My prof doesn't give a crap. That's good, that's good. 4 dogs named Astro, Balto? Clifford and Doug play tug of war with a toy. Astro pulls on the toy in direction of this degree. Balto? I'm gonna call him Balto. I think that's how you say it. Balto pulls the direction 6 degrees east of north, and Clifford pulls on the direction of gamma 55 west of north. Astro pulls strongly with 160 units of force, so newtons, which we abbreviate as A 160N. Balto pulls even stronger than Astro with a force of 200 newtons, and Clifford pulls a force of magnitude 140. When Doug pulls on the toy in such a way, his force balances out the resultant of 3 other forces, okay? The toy does not move with any direction. How big of a force in what direction must Doug pull on the toy for this to happen? So, let's write out Astro, so we'll just use A. 60 newtons. And 55 degrees south of east. And then we got Bolton 200 N with 60 degrees east of north. Clifford 140 N with 55 west of north.
Oops.
What and how big a force in what direction must Doug pull on the toy for this to happen? So I guess we don't know what D is. So here we have the little diagram of the cute little dogs pulling in all their directions. So the strategy that they say of how we should solve this is assume that the east is the direction of the positive x-axis and the north is the direction of the positive y-axis. This is used as in the example like a long time ago. We have to resolve the 3 given forces. So we got A from Astro pulling this way, B from Balto pulling up this way, got C from Clifford, and then Doug is supposed to balance them out. And to scalar components, then find the scalar components of the resultant vector. When the force D from Doug balances out this resultant, the sum of D and R must give the null vector. So that's when they should all equal 0. This means that D is negative to R, so the pull from Doug must be anti-parallel to R. So let's find what the components are of this. So similarly to the other example, you kind of just do like the same thing. So we got the AX and 160 cosine -55. I guess the hardest part for me for this question, when I look at it, is sort of making this diagram. I struggle a lot with directions, and I don't necessarily mean like degrees, like the actual number. I just struggle reading south of east. Like, when I see south of east, I'm like thinking, okay, you go south of east. Does that mean like you go to the south and go east 55, or is it east and then go south 55? But I always get those confused. But I guess drawing it out like this really helps. So south of east. So you go to east and you go south of that, so 55 degrees south. And then you get a bunch of these numbers. So very, oops. Should be A, Y. Very, very similar to the previous question. Or the previous... No, why am I writing B? I'm thinking of A. My migraine must be killing me. So you just do that, same thing, so we get bx 200 cosine 60, a bunch of other stuff, and then we'll end with cy is 140. We got sine of 55 west of north. Oh, so it's not 55. West to the west of north. So 55 from the west north. So it's 90 plus 55. Which is 145. Does that match? Yes, it does. It does match. So we get all of these answers. Then we can get the resultant. So we just add it all together. So far, is this like making some sense? Like, can you follow along a little bit? Newtons and 49 plus 2 newtons. And then once we put that together into an R, get 150.3 I hat plus 49.2 j hat. We can just put a negative sign on all of them, and then we can get where Doug is going. Negative 53 I minus 49.2 j hat. To find the magnitude, right, it's just like the Pythagorean theorem, so magnitude of D, so we get that, 150.3 squared plus 39.2. So this, just like the other, all of these operations, is just trigonometry, so you want to find that like hypotenuse. And from that you can get 158. And then to find that angle, this angle, so you have the magnitude, but you don't know the angle, and you have each component. So we have like the 150 something and the 49.2 here. You can get the angle by going tangent, but okay, I'm not blocking it. My head's not blocking it just yet. Tangent of the 49.2 over the 150.3, and then you inverse tangent, and then you can get some 18.1. Oh, yeah. It's good practice to put the negatives, but I knew that the negatives were going to cancel out, so I didn't include them. But yeah, don't forget the negatives. If you're lazy like me and you know that they're gonna go away, you can take them out. But if you're someone who is a little forgetful, which is also me, you should probably keep the negatives in, even for the magnitude, which I did not do. Oops. Alright. Is it often with direction? Because my studies have been degrees and clockwise or counterclockwise. It can be counterclockwise and counterclockwise. The way that they just wrote out this equation was with direction, because they just had a bunch of dogs pull rope, a tug-of-war game, four-way tug-of-war game in different directions. But with clockwise and counterclockwise, actually I find it a little bit easier. Because they'd probably just give you something and be like, okay, it is at the angle here, which would be 180 plus 45, right? So you just add those two. But either way, it works. So what happened with this specific question was it said, where was it? It said 55 degrees west of north, so up here. That in the sort of unit circle, so unit circle always goes this way. So we got our 90, our 180, 270, and our 0 and 360. So when it says 55 degrees west of north, that's an 8, that's not a 6. That's a 0. Okay, that's a 0. It's equivalent to the 145. This is 145 or 55 degrees west of north. So this is the same. This is how I see it. The hardest part for me is, like I said, deciphering what west of north means. But yeah, you're absolutely right. It can be telling you, well, like, let's say it's going 45 degrees counterclockwise from its origin. And then you just say, well, if it starts here, that means it goes around this way. Right? No, the other way. Counterclockwise is this way. So it goes like 45 degrees this way. So it would be like here. And then you could find that angle based off of the 2270. Alright. I'm gonna take a sip of water because my voice is starting to go out. It always starts to go out at like 1:30 when a minute or an hour and 30 minutes, roughly around there. They give us so many examples. How many examples do we have to go? We're almost done, but they're just examples. Alright. Example 2.1. There's a check your understanding. But maybe I'll go back to it later, and we'll finish all the examples first, because my voice is starting to go, which sucks. I hate that. How do okay, I have like such an admiration for other VTubers who can just yap for like 5 hours straight. I'm like, how do you do that? How do you not get tired? Usually when I play a game, it's much better because the game allows me to rest my voice in between. But when it's just sort of like talking all the time, I don't know how people do that. We have to find the vector of C that satisfies this equation. So do A B plus 3C to J, where A is 1 cat or 2K cat and B is this. And Thank you for the sub or the follow. Thank you for the sub or the follow. Sorry, I missed it. Although I think it was a sub on YouTube. But thank you for the sub on YouTube. Welcome to the strawberries. So we have this. So we first should like plug everything in. And that is exactly what they did here. Oh, no, they didn't do that there. So the isolated C first. I guess either way would have been fine. We'll do it the book's way, because it's the book, and I'm following the book. But we'll isolate C, so we'll take C on one side, which means we take... that should be a hat. This is a hat. 2J plus 6B minus 3... minus... No. Yes, minus 2A. Like that. Should be like that. Right? Yes, I just did it the other way. But it doesn't matter. So we'll have this. 2 over 3 plus... so we know that 6 over 3 is 2. So we'll just get 2b minus 2 over 3a. Then we'll plug the stuff in. So we'll have... I'm just gonna write it like this. Like that. And that should be a j hat. 2 over 3 j hat plus 2b. So I'm going to combine a lot of steps into one, which means we get negative 2 j hat plus k hat minus a. So with that we get 2 over 3 I hat minus 4 over 3 k hat. And then we combine all of that together, which would 12 4 okay, 7k, right? Because we have 2 pluses. Okay, let me write this out nicer so that it looks better. It's kind of a mess right now. Oh. To get 2. J. And then we have negative 2 over 3, not 3, plus k plus 4 over 3k. And because of that, we can rearrange it to be 2 over 3 I hat. So it's 4 over 3. Yeah, because we'll change this to a 6 over 2. Subtract the 2, then we get 6 over 3. Sorry. Change this to a 6 over 3, subtract the 2, then you get 4 over 2. And that would also be a negative. And then we can add that, so that would be 7 over 3 k hat. And then from this, you want to get the magnitude. You just do that Pythagorean theorem again twice this time. But when it's twice, you can just include it into the equation here. There we go. And this is your magnitude of... I guess they did not use a calculator this time. They just left it as 23 over 3. So this is your magnitude of that c-scalar. And this is your c-scalar as well. Right here. So here is your final answer. So, I guess basically with this example, all you need to do is try to find what C is, and you can sort of just use basic algebra. All you really need is basic algebra, and you just plug in the components. The hardest part is just that one variable has multiple components. So as long as you keep track of all the components and you know where to add them and combine them with, so like keep track of all the k's, the i's, and the j's, and make sure when you put that into the vector that it's like all together. But yeah, that's the hardest part and of this question. And just remembering that to find the magnitude, you can just use the Pythagorean theorem twice, or equivalent to this equation here to get that magnitude. Okay. Sorry. Skier, we're gonna calculate the displacement of a skier. How many more examples we got? We got this one, so 1, 2, 3. We got 3 more examples, and then we're done with this section. And then the next time I'll finish 2.4, which I think is multiplication. And then after that, we can finally move on to 2. Hold on. I think we're gonna move on to more kinematic stuff, which is good. These are a bunch of questions. Motion along a straight line. Yes. So we can finally move on to position, displacement, and velocity. Let me scroll up. This book is actually, I think this is a great resource if like you want to relearn physics, and it's open source, so it's completely free. It should be pinned or in the description, depending on where you are watching. But yeah, we're almost done with this section, which means we're almost to position, velocity, and displacement. Which I think feels, that to me feels more like physics. This kind of just feels like annoying math that you need to learn to do the physics. But it's still a good review for me, certainly. Wish there were more VTubers teaching physics, for real. I actually know, there are quite a few. Let me list. I know she has quite an audience. She is an astrophysicist, and she is super cool. Let me get her name. Her name starts with a Z, and it's like, I don't know how to pronounce it properly. It's not, her name doesn't start with the Z, but people call her Z. It's like, Sygy Altair. So it's Syzygy, and then Z, and then Altair. She also teaches math too, and cool stuff. Her stuff is more like video based, so you can always go back and like rewatch it. But yeah, her stuff is really good, and she plays violin. She's really cool. So call her Z, but her channel is Syzygy Altair, so Altair, and she's on YouTube. But she's really cool. Starting at a ski lodge, a cross-country skier goes 5 kilometers north. So let's write that down, 5 kilometers north. And 3 kilometers west. And then 4 kilometers southwest. Before taking a rest, find his displacement vector relative to the lodge when he is at the rest point. How far and in what direction must he ski from the rest point to return directly to the lodge? Strategy. We assume a rectangular coordinate system with the origin at the ski lodge, and with the unit vector I pointing east and the unit vector j pointing north. There are 3 displacements, so d1, d2, and d3. We identify their magnitudes as what they said, so all of these, and then we can identify their angles based on the compass again. But this time it's easier. So you got north, which is 90 degrees. We got west, which is 180, and southwest, which would be 45 plus 180, so that is 225. Yeah, I can do math in my head. I have a brain. So we got this one here, 225. I can solve the displacement. So similarly to all the other ones, you find the x and y component. I don't like how they call it d1, d2, d3. I'm still gonna call it a, because I think calling a, b, and c helps me get it less confused. So we'll have ax, we got is equal to 5, that's their kilometers, cosine 90, because that one is going north. And then we get our answer. That one I do know is 0, because cosine of this is 0. Cosine of 90 is 0. And the sine would be 1. So we got y, 5. I'm like remembering my unit circles of the like degrees. So that would just be 5. And we got b. That's not an a, it should be b. bx, which is 3, cosine. What was it, 180? And that one should be -1, because it's at the 180. It's 3. And then same thing with the rest, so continuing on, I guess this would be 0. Cx and cy. And then they got 2.8 and -2.8. Okay. Then we do the same thing where you add it all. So get all the x components, and then we get -5.8. My head is blocking. Sorry. All the x, you get 5.8 kilometers, and you do all the y's, so that is equal to 2.2 kilometers. Then you can get your total displacement. So this is how far that skier went from the lodge. .2 j hat in kilometers. And then to find his way back home, so we go anti-parallel to this. So, oops, go backwards, I guess. Go anti-parallel. So, anti-parallel, we just take that, what should I call this? S. We'll call this S. 5.8 I hat minus 2.2 j hat. Yeah, so this is how to get back. And if we want to find the magnitude, same thing. We just do that like Pythagorean theorem again, so that a squared plus b squared. So we get 22 squared, or 2.2 squared. 6.2 kilometers. And then once again, to find that angle, we just do the tangent. So we have the 22. Don't forget the signs in this case, because they are different. And then we got tangent is equal to that. So they said there for the lodge, he must go 6.2 kilometers in a direction of 21 south of east. So we get our 6.2 kilometers from that magnitude and our direction from this angle, which they said was -20.8. Significance. Note that no figure is needed to solve this problem by the analytical method. Figures are required when using graphical methods. However, we can check our solution makes sense by sketching it. This is a useful final step in solving any vector problem. So I don't have a protractor, but what I can do is I can draw a really, really bad, a really horrible diagram. So let's just say the origin is here. Our little our skier. I'm gonna make the skier light blue. Let's say the skier is me. I ski north 5 kilometers. So let's say this is 5 kilometers. I go here. I go west 3. So I go like here. 3. That'll be 3. And then I go southwest. So I go down here. Like 4. Do not look at the length. They're not to scale. And then if I want to go back to the place, I kind of just go that way. So yeah. Does that seem correct? Right? Yeah? Yes, okay. Because for the going this way is D, which makes sense. I'm going up and to the left. And you can tell that because I'm going left because of the negative, and I'm going up because of the positive. And if I want to go the anti-parallel direction, which is this way, I call that S. I'm going to the right, which is positive, and I'm going down, which is negative. So that does make sense. Yeah. And I'm also going at a negative angle. So if you like draw a circle like this, I'm kind of going like negative 20 degrees. That makes sense. All right. Displacement of a jogger. So a runner, person who runs and goes outside. I could never. Example 2.13. A jogger runs up a flight of 200 identical steps to the top of a hill, then runs along the top of the hill 50 meters before he stops at a drinking fountain. His displacement vector from point A at the bottom of the steps to point B at the fountain is that. So we have 200 steps up. Flight of 200 identical steps to the top of the hill. Okay, 200 steps up. I'm just gonna be like that. Then runs along the top 50 meters. So 50 along the top. Before he stops and drinks from a water fountain, his displacement vector from the top... his displacement vector from point A at the bottom of the steps to the steps at the fountain is that. Okay. Yes. I mean, you get that because of these. So this is where his displacement is currently when he's at the fountain. So put at the fountain. We have this with A, B, and negative 90. Plus 30. Hat. What is the height and width of each step in the flight? What is the actual distance the jogger covers? If he makes a loop and returns to point A, what is his net displacement vector? So the steps go at a diagonal. Oh, I see. So I see why this is negative now. I was like, I thought the flight of steps was like this way. Oops. Was like this. So I was like, why is it that negative? But I'll trust it. And it's because it's the other way. I should have looked at the diagram first. So go up flights of steps. goes up the flight of steps, goes to this point, and then runs that 50 meters along the top of the hill. So I really should rewrite that as this. Alright, from this, the displacement vector, DAB, is the vector sum of a jogger's displacement, DAT, along the stairs, from point A at the bottom of the stairs to point T at the top of the stairs. His displacement vector, DTB, so at the top, right here, at the top of the hill, we must find the horizontal and the vertical components of DAT. So that's how we can get the steps. If each step has a width and a height, the horizontal component of DAT must have a length of 200 in the width. And the vertical component must have a length of 200 height. So this is the 200, it comes from the 200 identical steps. So these are the steps. The actual distance of the jogger covers is the sum of the distance he runs up the stairs and the distance of 500 that he runs along the top. So from this, we sort of like break it down. So he goes DAT, then DT, was it B? Did you name it B? Yes, DTB, okay. This is displacement DTB. So we know that this is simply running the left direction to the 50, because that is from, that is from this, so we can get negative 50. And I'm assuming it's flat ground, right? It didn't say that it wasn't. So it's like that. And this is what we sort of need. And we have that resultant vector for us. So, D AB is equal to D AT plus D T B. And if we want to find D AT, my ears are gonna block it. D AT. Take this, DB. Right? Am I doing this right? Yes, I am. Okay, so there's a subtraction here. And then we minus this. Yes, I am. Okay. Remember your signs. The reason why I got confused was I forgot about the signs. So this should be DTB. It should also have a vector plus DAB. So now we are matched with the book. Remember your signs. And then we have our, you can just plug in the equation, so we get negative 50, negative minus negative 50, which just becomes a positive later, but I'll leave that in like that. And then we have plus negative 90 I plus 30 J. And then from that we can get our the steps, that path of the steps. So D AT is equal to negative 40, because 50, 90, I, and then plus 30. 30J. So that is our, like, vector of the jogger going from here to here. Okay, and then from this, then we can get our width and as well as our height. So j is our height and I is our width, because I describes it running along the x direction. So as the picture shows, picture shows it like this. So this is like the -40. And this is our 30. And then from that, we can just take the 200 is equal to 40. Since you're not going to have like a negative width of the stairs, you make sure like it makes sense, I guess. You can't have a negative width of the stairs. So what they did was absolute value it. They took the absolute value of it. Okay, this one. They took the absolute value of it and found that. So our width was 20 centimeters. And then the height is the same thing. So they do 200, height 30. They got 15 centimeters. Yeah, and then from that, we can also find that distance, so that magnitude. So if we want to find the distance, we take the magnitude of it. 40 squared plus 30 squared. That is 50 meters. So that is the total distance that he actually runs. Sorry, not the total distance. That is the distance of this that he ran. This is 50, and this is 50. Oh, this is 50. So total is 100. Sorry, my bad. I made a mistake. So you take the 50 plus the 50, and 100 meters. In many physical situations, oh wait, I've skipped. When he makes a loop and comes back from the fountain to his initial position at point A, the total distance he covers is twice the distance, or 200 meters. However, his net displacement vector is 0, because when his final position is the same as his initial position, the scalar component of his displacement vector are 0. So what they're saying is, if the runner goes up, goes to the water fountain, and goes back down, his displacement is 0. So technically, his net displacement vector is 0, because there's no change. He didn't come from anywhere, or he went back to the same place. Therefore, he didn't move, so his net displacement is 0. In many physical situations, we often need to know the direction of a vector. For example, we may not know the direction of a magnetic field at the same point, or the direction of an object in motion. We have already said directions is given by a unit vector, which is a dimensionless entity. That is, it has no physical units associated with it. When the vector in question lies along one of the axes in the Cartesian system of coordinates, the answer is simple, because then its unit vector of direction is either parallel or anti-parallel to the direction of the unit vector of an axis. For example, the direction vector d, so -5 meters in the I component, is the unit vector d -I. The general rule of finding the unit vector v of direction for any vector is to divide it by its magnitude. Okay. So if we want to find the unit vector v of the direction of any vector, we divide that by its magnitude. Okay, yeah. I feel like an example will help for this one. And I guess that's our last lesson and our last example for this section. And for today. And my voice is going. Now we're back on science. Great. Oh, you deleted your message. Sorry. Sometimes it takes me a little bit of time to see people's messages. But yes, we are back on science. I was debating whether or not to have this stream now or have it next month, but because next month I will be super busy and like on hiatus for a week, and my times will not be easy. I decided to have it now, but I have this content I have like a physics learning stream at least once a month, and I also try to incorporate other things into my stream as well. I have this game called Hacknet. I want to play it. I think you learn a little bit about coding, and I'd love to play that game. And I have it. I have the game. It's just I need to finish so many other games first. And Baldur's Gate. I have not played Baldur's Gate in a long time, and I miss playing it. And yeah, so hopefully I'll be able to do another physics stream for June, but if I don't, there'll definitely be one at the beginning of July. Alright, what am I doing? Okay. Question, answer simple because its unit vector of direction is either parallel or antiparallel to the direction of the unit vector of an axis. For example, okay, the general rule, finding the unit vector v. So finding a unit vector v of direction for the vector v, just divide by its magnitude. Divide by its magnitude. And get v equal to this over that. We see from this expression that the unit vector of direction, so that would be the v hat, is indeed dimensionless because the numerator and the denominator have the same physical unit. In this way, equation, right here, the highlighted equation, shows us to express the unit vector of direction in terms of unit vectors of the axis. The following example illustrates this principle. So we have that big vector. If the velocity vector of the military convoy is that, what is the unit vector of its direction of motion? Okay, so we are given 2.14. We're given this. I don't like all the zeros. There's too many zeros. It makes me confused. .1 K. So we have this, and then we want to find what the unit vector of its direction of motion is. So the strategy, they say, to figure this out is the unit vector of the convoy's direction of motion is the unit vector v, and then we have our little hat. So the unit vector v that is parallel to the velocity vector. So the unit vector v that is parallel to the velocity vector. The unit vector is obtained by dividing the vector, so this vector, by its magnitude. So basically, we just do this, and we plug in the equation. So to get our velocity, we do that like Pythagorean theorem thing again. So we got 4 squared plus 3 squared plus 0.1 squared. And then you get that your velocity, which they say is 5.001 kilometers per hour. Yeah. Okay, and then we take the whole vector, so v1, so that 4i, let's the 4i plus 3j plus 0.1k over our magnitude that we just found out. So we get 5.001 km over, oh, don't forget the units, which I did. Do as I say, not as I do. We take that, and then we just simply divide all these numbers by that 5.001 km, and then we get this. Uh, 0.79. 77998 I plus 5. No, I don't like how they wrote it with the 10 and the -2 outside. So I'm gonna write it the way that I think it should be written. Like, you're right in the fact that it's like in scientific notation and the significant figures look better and all that stuff, but still, I don't like that. I'm not a physicist, I'm an engineer. I like to make things easier, not accurate. I like to make things easier, not accurate. So here is our unit vector. Our unit vector, the direction of motion, and our unit vector. So this is our answer. Significant. Note that when using analytical methods with the calculator, it is advisable to carry your calculations to at least 3 decimal places, then round off the final answer to the required number of significant figures, which is the way we perform calculations in this example. If you round off your partial answer too early, you risk your final answer having a huge numerical error. It may be far off from the exact answer or from a value measured in an experiment. So that is how you calculate the unit vector. Verify that the vector is obtained. This equation. If the convoy was moving across a desert flatland, what if the third component of its velocity was 0? What is the unit vector of its motion? Which geographic direction will it represent? So wouldn't that just mean that this is 0? Yeah, I don't know. Well, that is the end of this. This section. This is how our notes. A lot of examples this time. There wasn't much new information. But holy crap, that is a lot of examples. I don't like how they don't round it to the 5th first time. Oh, like, you mean the 5 here? Like, you should round it to the 5? Yeah, sometimes I will say, I don't really like how this book goes about with its numbers, because I don't think realistically, well, it depends on what you study and do. But yeah, so here's this stuff. Next up we have product of vectors, and we'll be doing that next time, although I think this section is really, really long. So maybe I'll split that section up into 2. Depending on how long it takes me. But yeah, I'll go through a quick review of what we learned, and we'll see what happens. So we have vector addition multiplication. It has a bunch of properties that is very similar to addition in algebra. A null vector is when everything is like 0, and that is when 2 vectors are equal to each other if you take the difference. You can just add a bunch of vectors together, and that is like the summation. Remember, a summation, the symbol is not at all scary. It's just, there's a starting number, there's a number that you're going to end at, and you just add it all together. A strategy that I found to be very useful for solving the examples was to draw out a little triangle as well as a compass, if the question asked for it. Draw out the little compass. And the triangle, use cosine and sine to find the x and y components if it is a Cartesian coordinate system. then from that, you can basically just use algebra to find your answer. The only difference with using vectors from regular algebra is that imagine that a variable has two components, and those two components in that variable are kind of their individual variable in itself. So basically, one big variable has two things, and those two things can be moved around like other variables. But like you have to make sure that's included. But yeah, basically it's a bunch of trigonometry, a lot of algebra, and that's about it. I'm excited for learning cross products. It's been a long time since I've done that, and learning about dot products. But yeah, maybe it'll teach us about matrices? No, I don't think so. Okay, well, it'll be interesting. I haven't done a cross product or a dot product in a long time, and I'll learn that next time. But sorry, my voice is starting to like go out. I will have a stream on Monday. I'll be playing Sumide, which is that game that I thought was supposed to be cute, but was a little bit scary. I think we still have an hour and a half or 2 hours of that game, and then Thursday I'll be playing Baldur's Gate. And then after that, I'll be doing other things. I really want to start playing Hacknet. I do think it's going to be hard. And then at the end of June or in early July, I'll have another one of these physics learning streams. We'll go very slowly, so never feel like you need to learn something, or you can just pop in and say hello. Hopefully you learn something. My goal of streaming is to make people happy and to hopefully inspire someone to learn something new. Just even if it's one thing, I'll be happy. But yeah, I will be finding someone to raid on Twitch. But thank you for, oh, another thing I should say, thank you for following, for all the new people that are here. Welcome to the Strawberries, or thank you for subscribing as well. I really appreciate it. I am very happy that I get to do this. And yeah, I don't know what to say. Oh, I met my 130 gold follower on Twitch. I am trying to become an affiliate because I want emotes and I want channel point redeems. YouTube kind of sucks in that way that you need the threshold for getting, I guess the equivalent of a Twitch affiliate is a bit harder, but it happens when it happens. Okay, but yeah, I will stop yapping and find someone to raid. I do think someone will be on. But it seems like a lot of people are interested in science VTubers. I know that there's a whole group of VTubers that focus on science-based things. I think they're called V Theorem. That's what they're called. So check them out. They don't necessarily just do physics. One of them is like into like plants and like I think yeah, they do like the study of plants, and I think that group is really cool. Okay, I'll stop yapping. We're gonna go over to my friend, the Sky Globe. She's playing Overwatch with another one of her friends. If you would like to join in the raid, that'd be much appreciated. However, if you can't or just simply don't want to, no pressure. Feel free to, you know, go get some rest. Especially if you need to study, go study. Get some water. We do have a raid message, but yeah. Alright, let me switch over to the ending screen and then we'll raid. So we'll raid in a few seconds. We'll raid in 9, 8, 7, 6, 5, 4, 3, 2, and 1. Beep boop. Bye everyone. Bye bye.